Hello, and welcome to the polynomial division video. Congrats on making it to the end of the algebra video playlist. And today we're going to have a lot of fun dealing with something that looks a little tricky, but once you get the handle of it, is going to make you feel like you are a math wizard. So in the advanced algebra video, we briefly touched at the very end on how to handle polynomial divisions. So divisions with one polynomial divided by another polynomial. In the advanced algebra video, we covered how we could factorize the top polynomial in order to simplify by hopefully canceling out the bottom term of the fraction. But not all fractions play nice. Some of them will be resistant. You might have the top be hard to factorize, or it might be that the bottom just doesn't get canceled out. So what do? Well, in today's video, we're going to figure out polynomial long division, because sometimes we just want to simplify polynomial fractions. And then, once we've gotten used to simplifying polynomial fractions with long division, we'll figure out how to use that to factor higher order polynomials. If you remember, the advanced algebra video covered how to factorize polynomials of order 2, meaning that the highest power is of an x squared. Here we're going to learn how to do long division to help us figure out how to factorize things or polynomials of order 3 or higher. Once we finish doing that, we'll leave aside the polynomial long division to talk about partial fraction decomposition. So with the partial fraction decomposition, what we're going to do is the opposite of long division. What we are going to do is turn one big fraction into easier or smaller fractions. So instead of having to work with one big ugly term, we could break it up into a set of smaller fractions which are adding and subtracting each other, but at the end of the day are equivalent to the one really big messy looking fraction. And that is actually going to lead us to some future calculus applications where we're going to do stuff like integrals, we're going to do stuff like derivatives, and we're going to find that one big ugly fraction is going to take us up way more work than a series of small fractions. So that's what the aim of today's video is. We're going to figure out long division to simplify fractions and then use that to factorize higher order polynomials other than 2, because remember that the quadratic formula only works for order 2 polynomials. And then we'll do partial fraction decomposition, where we'll have one big fraction and turn them into smaller fractions. So with all that, I'm excited to get us started on something that's going to make you guys hopefully feel like you're on top of the world the way I did when I first figured out how to do all this stuff. All right, so polynomials are very useful in math, physics, engineering, stats. They pop up all over the place. And a lot of times we'll have one polynomial being divided by another polynomial. So let's say, for example, that we have something that looks like x cubed plus 6x squared plus 11x plus 6 being divided by x plus 1. Now, in the advanced algebra video, we saw that we could take a power of 2 or a polynomial of order 2 up top, factorize it, and then cross our fingers and hope that one of the top factors looked like the bottom factor so we could cancel it out and get it to work nicely. But the moment that we start running into powers of 3 or higher, our usual factoring techniques kind of start to break down a little bit in that they become really difficult to use. So we're going to figure out how to deal with this as an actual division instead of just treating it like a fraction whose terms we can cancel out. So I'm going to rewrite this division so that it looks like this. We're going to have x plus 1, nice and handy, and then we're going to divide it by x cubed plus 6x squared plus 11x plus 6. So in this notation, the thing that's inside of the actual, or that's underneath the long horizontal line, is the top of the division. And the term that's hanging out by itself on the outside is the bottom. And there's a simple little algorithm that we can use to figure out what this whole thing is actually equal to. So the idea behind this is that we divide by the biggest power of x, and we compare the biggest power of x with the biggest power of x underneath. So we're comparing the two, and we're asking how many times does the smaller one fit into the big one? Or in other words, what do I need to multiply the little one by to make it look like the big one? All right, so we're going to get started. So the question becomes, what do I need to multiply x by to make it look like x cubed? Well, the answer is actually x squared. So if we multiply x by x squared, we'll get an x cubed. So we'll multiply everything on the left, or the thing in the bottom, by what we need to make the biggest x term on the left look like the biggest x term on the right. So we're going to do x times x squared. Well, that's going to be just the x cubed. And then we actually have to multiply everything on the left-hand side. So we multiplied the x to give us x cubed. We multiply x squared by the 1, and it's a positive 1. So we're going to have positive x squared. Now, you'll know that you did this step right if the biggest power of x in black is equal to the biggest power of x in blue. And what we're going to do is we're going to take this little term that we got by multiplying the thing on the left by the term on the top, and we're going to subtract it. Now, in this case, we are going to have a lot of negatives and positives floating around, and it's really easy to make a mistake when you've got a lot of negative signs floating around. So I highly recommend putting brackets down to remind yourself that we're subtracting by this entire term. Because without the brackets, we might forget and think that the x cubed is negative and that the x squared is positive, when in reality, because we're subtracting the top by the entirety of the bottom, it's actually every term inside these blue brackets that is being affected by that negative sign. So we're going to have x cubed minus x cubed. Well, that's just going to be 0. Boop. And then we're going to have 6x squared minus x squared. So we've got 6x squared minus 1x squared. Well, we're going to have ourselves 5x squared. Now you notice we're trying to make the biggest power of x in black on the outside look like the biggest power of x on the inside, because when we subtract, we chip away. So whereas before we had a power of x to the power 3 as the biggest, we now have it just to the power of 2. So we're going to drop down the next term. So we've got the 6x squared was minused by the x squared, so now it's just a 5x squared. We haven't done anything to the 11x, so it just drops down and stays 11x. Now, the next step, again, like the previous step, is how do we make the biggest power of x on the outside look like the biggest power of x on the inside? Well, I want to make x look like 5x squared. Well, I see there's no 5 in front of the x over here, so I'm going to have to throw down a 5, because now I've got something that looks like 5 times x gives me 5x, but I want it to look like 5x squared, so that's telling me that I'm missing one x term. So now if I take 5x and I multiply by x, I'll get 5x squared, which is what I want. So let's do that. We're going to multiply the next blue term by the black term on the outside. We're going to do 5x times the x. Well, that's just going to be 5x squared. And then we're going to multiply the 5x by the 1. So 5x times 1, well, anything times 1 is just itself, 5x. And then remembering that we're going to be subtracting, so I throw the brackets down and then put the minus sign in front so that I remember that every term in the blue is being affected by that minus sign. All right, so we'll do 5x squared minus 5x squared. Well, anything minus by itself is just 0. And then next, we're going to do 11x minus 5x. Well, that's just going to be 6x. And that's our little subtraction step right there. We haven't done anything to the 6, so now we drop down the 6. So now we have 6x plus 6. Perfect. And notice how we always have a 0 because we're always getting rid of that biggest power of x. So that's a really quick way to double check that you haven't made a silly mistake. We're always dropping down a power. So we started with x cubed, then x squared, and now just x by itself. Now the next step, like before, we ask how do we make the biggest power of x on the outside look like the biggest power of x on the inside? So in this case, it's 6x. I've got an x. Well, the way I do that is by multiplying by 6. Because if I take 6 and I multiply by x, I get exactly 6x. So let's do that. Let's multiply that newest blue term by the term on the outside. So we're going to have 6x, and then 6 times 1 is 6. Again, we throw the brackets down. We put the negative sign to remind ourselves everything's being affected by the minus sign. And then we ask, what's going on? Well, 6x minus 6x, well, anything minus by itself is 0. 6 minus 6 is 0. So we end up getting 0. So that tells us that our original division actually divides perfectly because there's nothing left over. This right here is what is left over after our division. I like to think of it as the polynomial equivalent of a decimal point. So sometimes when you divide, you get decimal points. And sometimes when you divide, you don't get decimal points. This is one of those nice cases where we don't have decimal points. So we have this whole work over here, but what does it actually mean compared to what we started with? Well, what this algorithm, this long division of polynomials has shown us is that this original expression, which is a little frightening at first, and I'm saying that as someone that likes math, this looks not great, not just because I'm bad at drawing, and that is actually simply equal to x squared plus 5x plus 6. And now this is a polynomial of order 2. And we already have a whole video we already have a whole video that shows us how we can work with polynomials of order 2. We could factorize it really quickly. If we wanted to solve and it happened to be equal to 0, we could do our little factorizing step to solve the equation. And it actually ends up being not too bad. So just by looking at this polynomial, I already know, okay, well, that's just going to be x plus 2 times x plus 3. And then you guys can go through the expansion and find that this expression is the equivalent to that expression. And now if we compare, x plus 2 and x plus 3 to the original monster, well, it's quite clear to me which one I'd rather work with. I would much rather work with this little guy over here as opposed to this behemoth of a polynomial on the left-hand side. All right, so we're going to jump into another example where we'll actually have a remainder left over so we can see what that looks like. So in the last example, we handled polynomial long division. That was a nice division with no decimal points. But not all fractions are nice. Some fractions will give you decimal points. And this is one of those cases where this fraction, or in other words, a division, ends up with the polynomial equivalent of some decimal points. So we're going to start off again with a polynomial. This time it's going to look like 2x squared plus 8x minus 6 being divided by x minus 5. Now the top one we could actually probably factorize, and then we'll find out that nothing cancels out. So we're going to end up stuck with something that's not very useful. And here's where long division shows its true colors. Even if we factorize the top and it doesn't cancel out a bottom term, we can still make the actual expression easier to work with. All right, so remember this division right here with our new notation, we're going to have x minus 5 on the outside because that's the bottom, and then we're going to have the inside. We're going to have 2x squared plus 8x minus 6, and we are dividing by. So same thing as before, we want to ask how do we make the biggest power on the outside look like the biggest power on the inside? Well, I see that the outside doesn't have a number in front of the x, and this one does. So I'm going to really quickly throw in the 2. This x is of power 1. This x is of power 2. So I know I'm missing one more extra x, so I throw down the 2x. So now I multiply the newest blue term with the outside term. So 2x times x gives us 2x squared. Because I multiplied, I have to multiply the whole thing. So 2x times the minus 5x gives us minus 10x. All right. And then we throw the brackets to remind ourselves that when we subtract, the minus sign affects everything inside the bracket. So we're going to have 2x squared minus 2x squared. Well, that's just 0x squared. And then 8x minus 10x. So because we've got the minus and the minus, it actually turns it into a plus. Remember that two negatives turn into a positive. Those two negatives cancel out. So in reality, we're going to have 8x plus the 10x, which gives us 18x. And then we haven't done anything to the 6 yet, so we drop her down, and we get minus 6. Now the question becomes, how do we make the biggest power of x on the outside look like the biggest power of x on the inside? Well, I see that there's an 18 over here and there's a 1 over here, so I'm going to really quickly throw down an 18. The highest power of x is x to the 1. The highest power here is x to the 1, so I don't need to add any powers of x's. It's actually good enough as it is. All right, so now I do the same thing as before. I take that newest blue term and I multiply by what's on the outside. So I'm going to have 18 times x. Well, we're going to have 18x. Next, we're going to have 18 times negative 5. So here again, got to be careful of those little negative signs. They can really screw us up sometimes. And we're going to have 18 times negative 5, which is actually going to be negative 90. All right. And now we have the next two terms to work out. We're going to have, oh, sorry, I almost forgot. We need the blue brackets with a minus sign in front to remind us that the negative sign's affecting everything on the inside. So we have 18x minus 18x, and we've got a 0. You should always have a 0 as your first term. That lets you know that you did it right. And then we're going to have minus 6 minus 90. So that minus 90 turns into a positive 90, and we're subtracting 6 from it. So 90 minus 6 sounds a little nicer than minus 6 minus 90, but it's the same thing. 90 minus 6 will give us 84. Now in the last video, we stopped when we got to 0. Here, we don't get to 0. We get stuck with a remainder of 84. And if I ask myself, okay, well, how can I make x look like just 84? Well, I can't. There's nothing I can multiply x by to make it look like 84 in this type of algorithm. I could divide it by x, but that's not how this works. So right now, when you get stuck, when you get to a point where the outside power of x is bigger than the inside power of x, because in this case, the power of x is 0 since there is no x, we've gotten as far as we can get. So that tells us that we have basically the polynomial equivalent of 84 as a decimal point. So we've simplified it as much as we could. The blue term is the bit that managed to divide nicely, and then the 84 is the decimal point. So what does that actually look like? So what that looks like is that 2x squared plus 8x minus 6 divided by x minus 5 is going to look like 2x plus 18 minus, oh sorry, not minus, 2x plus 18, so that's the blue term, that's the bit that managed to factorize nicely, plus what was left over. Well, what was left over is the remainder, which is 84. And what we were originally dividing by was x minus 5. So we've turned one big nasty looking fraction into a nice little linear x term, and then one much simpler fraction. So even though we weren't able to get an exact solution because it didn't divide through nicely and we had a decimal point, this decimal point right here is still a lot nicer than the whole division. So even though it doesn't always divide out nicely, we still get a much nicer result than we would have had we not done it in the first place. And if we had simply tried to factorize the top equation, which is doable because it's only of power 2, we would have realized that there is no way to factorize in order to cancel out the bottom term. So if we did factorize the top, we would still get stuck. I mean, you would at least have done some factoring practice, which is nice, but you wouldn't have gone any further. You would not have made the fraction look any nicer. So my suggestion is, if you want practice doing factoring, for sure, factor, maybe it'll work, maybe it won't. Whereas the long division will always work. It will either divide super nicely like the previous example, or you'll end up with a remainder like we did in this example, but you'll still end up with a nicer looking expression. So when you're doing this on a test, or when you're just trying to do math for fun, just remember factorizing is a little bit riskier because it may or may not work, whereas this long division will for sure always work. Now we're going to change gears in the next example, and we're going to focus on how to do long division like we just did in order to factorize higher order polynomials. All right, so now we're going to focus on how we can use the long division that we learned to factorize high order polynomials. So let's say, for example, we had x cubed plus x squared minus 10x plus 8 equals 0. And we wanted to factorize this thing. Well, in the advanced algebra video, we saw how we could factorize polynomials of order 2, meaning that the highest power of x was a 2. But in this case, the highest order is actually a 3. So those rules that we had about multiplying and addition, they start to break down, and unless you have a very nice looking power of 3, it gets quite a bit trickier. There's no kind of tried and true method. There is one equation, but it is very long and an absolute nightmare to use, so it's not something that you can really do in a test setting. It's more something you can do when you're doing math for fun. So what do we do if we're in a test setting? We've got a power of 3 and we want to solve it. Well, again, when we wanted to solve those power of 2 polynomials, we made the polynomial equal 0 because the factoring would let us solve. The exact same logic applies. We've got a polynomial equal to 0. We're going to factorize it, and that'll let us solve it really quickly. But how do we factorize it? Well, one of the ways we can do a factorization of a power 3 is we can try and guess an answer, and then that'll give us one of the factors. And then that, in turn, will let us do the long division. Because right now I can't do long division. There is no division. So when you're trying to guess a possible solution, I would recommend starting with really easy numbers to check. So amongst the easiest numbers to check would be x equals 1. So if we threw in x equals 1, I would have 1 times 1 times 1. So this would actually just be 1. I would have 1 times 1, which again is just 1. I would have minus 10 times 1, which would be minus 10. And then this 8 doesn't have an x touching it, so it's just 8. And then we see here that we've got 1 plus 1 plus 8, which is 10, minus 10. So what we actually have is 0. 0 is 0, so it looks like x equals 1 is an answer. So when we're trying to guess this thing through, highly recommend you try out x equals 1, because I could have tried out x equals 5 first, but then I've got 5 times 5 times 5 plus 5 times 5 minus 10 times 5, and you're just making extra work for yourself, and there's really no point in that. So when you're trying to do the guess method, try really easy numbers first. So we know that x equals 1 is a solution, which tells us that the factor is x minus 1. Because remember, when we're factorizing, we're getting a series of multiplications that equal to 0. and we get 0 when x is equal to 1. So that means that one of these terms is x minus 1, because when x equals 1, you get 1 minus 1, turns this bracket into a 0, and the moment you have a multiplication by 0, it wipes out everything else, and we get 0 equals 0. We've got ourselves a solution. So just remember, the factor is a little bit trickier because it's not just as simple as, x equals 1, so the factor is x plus 1. No, that is false. X equals 1, so the factor is x minus 1, because we want the term to equal 0 when x equals 1. So that's just a quick little aside, because it's a mistake that I see happen a fair bit. So what does this actually mean? That means that I know that this whole big polynomial over here can be divided by x minus 1. So we're going to do the same thing we did last time. We're going to go x minus 1, and then we're going to divide by x cubed plus x squared minus 10x plus 8. And we're going to figure out what this is. So like before, we figure out how do we make the biggest power of x on the outside look like the biggest power of x on the inside. So we're going to have x looks like x cubed. Well, I've got a power of 1. This is a power of 3. That tells me I'm missing 2 powers. So this is going to be x squared. I multiply the newest blue term by everything on the outside. X squared times x, well, that gives me x cubed. X squared times minus 1 gives me minus x squared. And then we throw down the brackets and we subtract. X cubed minus x cubed, well, that just gives me 0. X squared minus x squared, well, the minus turns it into a plus, so it's actually x squared plus x squared, which gives me a total of 2x squared. Then I drop down the next term so that I can work on it next. All right, so now I have the same thing as before. I want to make the biggest power of x on the outside look like the biggest power of x on the inside. In this case, I want to make my x look like a 2x squared. Well, there's no 2 in front, so I know I need a 2 in front. This is x power 1, this is x power 2. That tells me I'm missing 1 power of x, so that's 2x. And now I can do, okay, the newest blue term multiplies the outside terms. So I've got 2x times x, that gives me 2x squared. Perfect. And then 2x times minus 1 gives me minus 2x. So what do? I throw down the brackets, and then I subtract. 2x squared minus 2x squared, well, that gives us a 0. Negative 10x minus 2x. Well, the minus turns into a positive, so I've got minus 10x plus 2x, which gives me minus 8x. And then I drop the plus 8, the next term down, and again, we do the same thing. How do I make the biggest power of x on the outside look like the biggest power of x on the inside? Well, I've got a minus 8 in front, so I'm going to have to throw down a minus 8. This is x to the power 1. This is x to the power 1, so no more x's. I'm already at the same power. And now I multiply the newest blue term by what's on the outside. So I've got minus 8 times x. That's going to be minus 8x. And then I'm going to have minus 8 times minus 1. So the minus and the minus turn into a positive 8. And then I throw down the brackets and subtract. And what we'll see here is something very cool. The term in blue is the exact same as the term in black. So when I subtract them, they'll actually cancel out, because I'm basically taking one term and subtracting it by itself. We can go through it the long way as well. Minus 8x minus 8x, so that turns it into a positive. So I've got minus 8x plus 8x, which is 0. And then I've got positive 8 minus positive 8. So that's 8 minus 8. Well, that's just 0. Perfect. So now I can say that x cubed plus 2x, oops, sorry, that was the wrong term. Now I can say that x cubed plus x squared minus 10x plus 8 looks like x minus 1 times the term in blue, because that's what we got after we divided the long term by the term on the outside. X squared plus 2x minus 8. And look at that. We have a scary looking power of 3 polynomial that looks like a simple power 1 polynomial, x minus 1, times a power of 2 polynomial, which is 2. So that's not too bad, because we can actually solve this right here in a multitude of different ways. We can do the generating of the list like we did in the advanced algebra video, where we know that our factors have to multiply to minus 8 and add up to 2. We can use the quadratic formula if we're feeling a little bit less inclined to do factoring manually. But we've got options. The thing is, we now have options. So what I can say really quickly is, okay, x cubed plus x squared minus 10x plus 8 actually looks like x minus 1. And then this term right here is going to look like x minus 2, x plus 4. Because x squared plus 2x minus 8 is actually equal to these two factors expanded out. And if you want to practice expansion, you can check it out and see that it's true. And if you want some factoring help, because this didn't quite make sense, I'd recommend checking that advanced algebra video where I cover that in depth. And so now we actually have 3 different factors that multiply to 0. So instead of having this really big ugly mess over here, I now have a set of 3 equations. I have x minus 1 equals 0, x minus 2 equals 0, and x plus 4 equals 0. Now again, would you rather try and solve the x cubed plus x squared minus 10x plus 8 term, or would you rather solve x minus 1 equals 0, x minus 2 equals 0, x plus 4 equals 0? Well, I know for me the answer is very clear. I would much rather solve 3 very simple equations as opposed to one big scary power of 3 polynomial. So we see here that we have very simple solutions, x equals 1, x equals 2, x equals minus 4. Whereas before, I wouldn't have been able to tell you, oh yeah, the answers to this big trinomial are x equals 1, x equals 2, x equals minus 4. But through the power of algebra, we were able to turn this scary looking power of 3 polynomial through the power of factorizing into very simple equations that you can solve just by looking at it. So from this case, if you're trying to factorize a polynomial of power 3, the first thing we did is we tried to guess a solution, starting off with a very easy number like x equals 1. Another easy one to check out would be x equals minus 1, but x equals 1 is even easier, so that's why I decided to do x equals 1 first. And then once you've guessed a solution, in other words, you get 0 equals 0, we now know what one of the terms has to be. So if x is equal to 1, that means that one of the factors has to be x minus 1. Because remember, with the factoring, we want the solution to give us a 0. And then once we have one factor, well, we can start to divide. We can divide the big scary polynomial by a factor that we know it has to have. And then we manage to break it down from a power of 3 into a power of 1 multiplying a power of 2. Once you have a power of 2, we've got a bunch of different factorizing tools at our disposal to break it down even further. And then at that point, our big power of 3 is just 3 powers of 1. And we get 3 simple equations, which in turn give us 3 simple solutions. So if you're wanting to solve, or if you're wanting to factorize a polynomial of power 3, just remember you can give yourself a polynomial long division by guessing an answer. that brings us to our next topic, which is how do we do fraction decomposition? All right, so far, all of the polynomial division that we've been dealing with has had a big divided by small. So by that I mean we've got a high order polynomial on top, just to give you an example, being divided by a smaller order. So here we've got an order 3 because the highest power of x is 3. Down below we have a power 1 because the highest power of x is 1. So we've figured out a couple different ways that we can do big divided by small. Sometimes it divides nicely with no decimal points. Sometimes it doesn't divide nicely and we end up with the polynomial equivalent of decimal points. And that's all fine and dandy, but sometimes we'll end up with a small polynomial being divided by a big one. And the moment that this is the case, the previous techniques that I've shown you, they fall apart. They don't work anymore. So this becomes a different case. So this right here, small versus big, will completely change what you have to do. So when we went from big to small, we would end up getting a fraction still. So we would have a big fraction into a smaller fraction. But from small to big, we can't get smaller fractions. What we end up doing is we get, one fraction and we split it into lots of small ones. So it's going to look a little different. Whereas here we would have, ax squared plus bx plus c divided by some dx plus e would look like some sort of either, fx plus g if it didn't have a decimal point, or fx plus g plus h over ex if it did. Oh, sorry, no, that would be dx plus e. So we can see how when we did the big versus the small, we would end up getting either no fraction at all, because it divided nicely, or we would end up with a couple of terms and a slightly smaller fraction in the big versus small. In the small divided by the big, what we'll end up getting is we'll get something that looks like ax squared plus bx plus c being divided by dx plus e, and it would turn into something that looks like a over dx plus e plus b over dx plus c. So the shape is quite different. Here, the purpose isn't so much we're just going to divide to get a nice simple fraction, a non-fraction or an easy term with one simple fraction. What we're going to do now is we're going to go one big polynomial. Oh, sorry, I should have put down a 3. Boop, 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 because remember, in this case, the one down below is bigger than the one up top. So what we're doing is we're turning one big fraction into a combination of smaller fractions. And the reason we do that is that later on in the future when we're doing calculus, it's easier to work with small little chunks than it is with one big one right at the end. Another way to think of it is when we were doing regular fractions, we would take two small fractions and combine them into one big one. Here we're doing the opposite, where we're taking one big fraction and splitting it up into smaller fractions. So we can think of partial fraction decomposition as the opposite of combining fractions. So in the fractions video, we saw how we could take an addition of fractions with different denominators and combine them through cross multiplication to get one big one. Partial fraction decomposition is basically the opposite, where we take one big fraction and we split them up into several smaller fractions. So I'm going to start off with a simple little example, and then we're going to work up in complexity after that, because there's going to be a couple of little rules depending on what the fraction actually looks like. So let's start off with something relatively simple. So we're going to have 3x plus 1 being divided by x squared plus 3x plus 2. Now, when we want to do partial fraction decomposition, the main goal is I've got one big fraction, I want to turn it into a couple of smaller fractions because the smaller fractions are going to be easier to work with. Or the other way we can think about it is we've got a polynomial division, but this time the big polynomial is at the bottom instead of the top. So now I've got a little one being divided by a big one. So what do? Well, the first step is always to make sure that the bottom one's the bigger one. And then once we've realized that the bottom one is the bigger one, what we have to do is factorize the bottom one as much as possible. So a quick little reminder, we have here x squared plus 3x plus 2 that we want to factorize. We need a multiplication up to 2 and an addition of 3. So that tells me really quickly our factors are going to have to be x plus 1, x plus 2, because 1 times 2 gives me 2, and 1 plus 2 gives me the 3. If that's a little confusing, I'd recommend checking the advanced algebra video. I've mentioned that a couple of times at this point, but it covers all of the factoring, and I don't want to waste too much time doing more factoring stuff. We've already covered it quite a bit in the previous video. So great, we now have an expression where we have a small polynomial being divided by a bigger one. The bigger one is factorized nice and cleanly, so we need to figure out how to split this up. So what we're going to do is something that we actually do a fair bit in math, where we want it to look a certain way, but we don't know exactly how it's going to look. So what we do is we go, okay, let's just say that it looks like this. Let's just say that it looks like a constant divided by x plus 1, and that it's being added to by another constant divided by x plus 2. So in this case, the things that we're actually looking for are a and b. We want to find values of a and b such that this expression is true. All right, so that's something that we actually do a fair bit in math. We say we want it to look like this, so we're just going to make it look like that. And now we're going to have to figure out what we need to happen so that it's actually true. So we've got our little expression here, and what we're going to do is we're going to take the whole equation and we're going to multiply both sides of the equation by x plus 1 times x plus 2. So on the left-hand side, the x plus 1 cancels out the x plus 1, the x plus 2 cancels out the x plus 2, so we're going to have 3x plus 1. On the right-hand side, we see that a is being divided by x plus 1 and then multiplied by x plus 1. So those x plus 1s are going to cancel, and we're going to be left with a times x plus 2. Next, we're going to multiply another term on the right side, the b divided by x plus 2, by the x plus 1 times x plus 2. I see that b is being divided by x plus 2, multiplied by x plus 2, so those two cancel out. And we're going to be left with b times x plus 1. Now, we've got ourselves an equation, and we can try and solve it and figure out what a and b have to be so that this expression right here is true. There's a couple ways to do it. We can either make ourselves a system of equations, which would use quite a bit of algebra, which I'm leaning towards because we've been doing a lot of algebra so far. The other way is by plugging in numbers. So we're going to do both ways, and then we're going to see which way you guys like best. So the first thing we're going to do is plug in values and see what happens. So when we're plugging in values, what we're going to want to do is plug in values that are easy to work with. So we look at the parentheses, and we want to make those zeros, because zeros are like the easiest numbers in the world to work with. So we'll start off by making the a term a 0. So let's plug in x equals minus 2. So if we plug in x equals minus 2 everywhere, on the left-hand side, we'll get 3 times minus 2 plus 1 is equal to a. Instead of x, it's minus 2 plus 2. And then b is going to be minus 2 plus 1. Because wherever we see that x, we replace it with minus 2. So on the left-hand side, we're going to have 3 times minus 2, which is minus 6. Minus 6 plus 1 gives me minus 5. A is going to be minus 2 plus 2. Well, that's just 0, so that completely wipes this out, right? So that's just going to be boop, 0. So we're going to have A times 0 plus, and now we're going to have B minus 2 plus 1. Well, minus 2 plus 1 is minus 1. So A times 0 wipes out. So we're going to have minus 5 is equal to minus B, because it's minus 1 times B. So then we get B equals 5. Hooray! Next, we're going to choose a nice simple answer. Sorry, not a nice simple answer. A nice simple value for A. So we put in minus 2 to cancel out this term. Now we're going to cancel out the B term. So we see x plus 1. We want this to be 0. So we plug in x equals minus 1. And when x is equal to minus 1, on the left-hand side, we're going to have 3 times minus 1 plus 1 is equal to A. And then instead of x, it's going to be minus 1 plus 2. And then we're going to have B, and then instead of x plus 1, we're going to have minus 1 plus 1. So 3 times minus 1 is minus 3, plus 1, minus 2. And then we're going to have A of minus 1 plus 2. So minus 1 plus 2 is just 1. So we're going to have A times 1 plus, well, minus 1 plus 1 is 0. B times 0 is 0. So look at that. We now have A equals minus 2. Now we know that our original fraction 3x plus 1 divided by x plus 1 times x plus 2 is going to look like A divided by x plus 1, where A is equal to minus 2. And then we're going to have B divided by x plus 2, and in this case B is 5. So we now have one big polynomial fraction divided into two smaller polynomial fractions, because we found the values of A and B that make this true. Now, this on the left-hand side is the guess number method. And the way we do it is by plugging in x values so that these bracket terms here and here cancel out. So we want zeros. So that's how we got x equals minus 2 as a number to try, and that's how we got x equals minus 1 to try. So when we're dealing with simple fractions, where the fractions down below are easy to zero out, the guess a number method works fairly well. There's another method that involves using algebra, and that one will always work no matter what. So let's do it. So we start off with the same expression up top, where we multiply both sides. So on the left-hand side, we're going to get, actually I'm going to change the colors. So on the left-hand side, we're going to get 3x plus 1, and that is going to equal, well, remember again, x plus 1 cancels, so we're going to have a of x plus 2 plus b, x plus 2 cancels, we get x plus 1. So the top is still the same. We still have 3x plus 1 equals a times x plus 2 plus b times x plus 1. So now what we do is we group together the x terms. So what do I mean by that? I mean that we're going to have 3x plus 1 is going to equal ax plus 2a plus bx plus b. So all I did is I just brought in the a and multiplied everything in the term, and then I brought in the b. So what we're going to do is we're going to split this up into two equations. We're going to have the x equation and the non-x equation. So for the x equation, we're going to have 3x is equal to ax plus bx. We see that there's x's everywhere, so we could cancel them out by dividing by x, and we get 3 is equal to a plus b. Nice and easy. Next, we give ourselves an equation by looking at all of the non-x terms. So we have a 1 on the left-hand side, and that's going to equal, well, I see the 2a here, doesn't have an x term, and the b term does not have an x in it. So here we get a nice simple 1 is equal to 2a plus b. Fairly straightforward. And the reason that we split them up is in order for this equation to be true, all of the x's, so the ax and the bx, has to equal 3x, and all of the non-x's, 2a plus b, have to equal 1. So the rationale behind it is a and b have to add up to 3 in the x case, and in the non-x case, 2a plus b has to equal 1, and we have ourselves a system of two equations. Now here, there's another two ways we can do it. I stacked one of the equations on top of the other because I realized that I've got a plus b and a plus b. So what I could do, I can straight up subtract both equations from each other to cancel out the b. So that's a fairly sneaky way of doing this. It's a little bit less rigorous. It doesn't always work because we don't always have equations that stack up so nicely. So if you wanted to do it, we can check really quickly. If we did the top equation minus the bottom equation on the side here really quickly, we have 3 minus 1, that's 2. We've got a minus 2a, that's just going to be minus a. And then b minus b is just 0, there is no b, so that tells us a is equal to minus 2. Nice and easy. So if you could stack the equations on top of each other and you notice that there's a really easy way to cancel things out, it's worth it. It doesn't always work, so I'll show you what happens when it doesn't work or when we don't recognize it. We can always fall back on substitution. So let's take a look at that red equation and let's solve it for a. So I'm going to take the red equation and solve it for a. So I've got 3 minus b is equal to a. So that's the red equation by just moving b over to the other side. And then what I'm going to do is I'm going to plug this value of a into the green equation. So I'm going to have 1 is equal to 2 times, and now wherever I see the a in the green version, I'm going to substitute in the red expression. So the red expression was 3 minus b. So that was 2 times a, but a is now 3 minus b from the red equation. And then add it to b. So what do I have now? I've got 1 is equal to, well, we'll multiply in. 2 times 3 is 6. 2 times minus b is minus 2b. And then I've got a plus b at the end. So that means that we're going to have 1 is equal to 6 minus b. Now we're almost done. Now we're going to solve for b really quickly. We're going to move b over to the left-hand side and the 1 over. So we're going to have b is equal to 6 minus 1. So b is equal to 5. And the nice thing about doing the substitution method is that I already have an expression for a. I already know from this term right here that a is equal to 3 minus b, but I already know what b is, which is 5. So I have 3 minus 5 minus 2, a is equal to minus 2. And just like that, I have expressions for b, I have expressions for a, and look at that. B is equal to 5, B is equal to 5, A is equal to minus 2, A is equal to minus 2. So no matter what method we use to solve, we still end up getting the same values for A and B. So on the left-hand side, because it's a fairly simple equation, we could plug in x values that gives us zeros and makes it easy to solve. On the right-hand side, which is the method that will always work, we use substitution. So first, we expand out the ax plus 2, the b times x plus 1. We split up our equation into two sets of equations, one with the power of x, one with the non-x's, and then we get nice simple expressions for what A and B have to be to make the blue case true. And then we've got two choices. We can either write one equation on top of the other, and then we find that there's a nice easy plus B. There's a nice easy term that can cancel, and we can just straight up subtract one equation from the other like we did in the purple case, and we get a very fast answer for what A has to equal. And then we can really just plug back in. So in the purple case, for example, we have 3 is equal to A plus B. Well, I already know that A is minus 2, so we're going to have 3 is equal to minus 2 plus B. So when we move the 2 over, we get 5 is equal to B. So even in the purple case, we still end up getting the exact same values for A and B. And then in the red and green case, we just have a system of two equations. We solve one of the equations for one of the variables. So in this case, we solve the red one for A, and then we plug the expression for A from one of the equations into the other equation. And now we have an equation that doesn't depend on A and B. The green equation now only depends on B. And then we can solve for B, and then the nice thing is, because we already solved for A, the moment we have an answer for B, it's just a really quick plug in the B for the expression of A, and now we've got both. So I decided to kind of give you guys a taste of all of the different ways that we can solve our expression at the top over here. So these two expressions can be solved in 3 different ways. Plugging in numbers to get values for A and B. We can give ourselves a system of equations by splitting up the x's and the non-x's, and then we can either subtract the equations from each other in the purple case, or in the case that there isn't a simple little subtraction or simple little one equation gets rid of a term in the other equation, we use substitution, where we take one of the equations, solve for one of the variables, then we take that same variable and plug it into the other equation. And then from there, we've got one equation, one variable. In this case, it was B. We solve for B. We can plug B back into A, and now we've got expressions for both B and A. So this might have seemed like a lot of work for one question, but I really wanted to show you guys that there's lots of different ways to do it. So whichever way resonates most with you, try doing that one first, because we're all different. Math is a language. Everyone has their own accent, and there's nothing wrong with that. So I wanted to expose you guys to lots of different ways of solving the exact same equation. So you can start to get a glimpse of the beauty of algebra, the power of it, the way it lets you do things the way you want to do it, so long as you follow the rules. So this was just a simple little example real quick of how we could take one expression of a small polynomial being divided by a big polynomial and then turn it into 2 small fractions. So the way that we combined fractions with different denominators way back in the fractions video, we can do the opposite. We can take a big one and break it into small ones. So there's always an alternate way. There's always an opposite. There's always a symmetry in algebra. We combined fractions with different denominators into one big one. We can take the big one and split them into 2 small ones with different denominators. So now that we've got this example out of the way, let's start to look at this thing a little bit more rigorously. So we're going to start to talk about the actual partial fraction decomposition rules, because what we do changes a little bit depending on what the fraction looks like, but the actual logic stays the same. So we're going to have some p of x, which is going to be a polynomial x, and then we're going to divide it by some q of x, which is another polynomial. So for example, it could be x squared plus x plus 1, and q of x could be x cubed plus 2x squared plus x plus 2. Just throwing out an example. So p of x is just some random polynomial, q of x is another random polynomial. The number one rule is p of x has to be smaller than q of x in terms of power. So the biggest power of x has to be at the bottom, no matter what. So for partial fraction decomposition, rule number 1, p of x has to be smaller than q of x. So the bottom has to be the bigger power. Rule number 2, q of x has to be factored as much as possible. So now, why am I making such a big deal about q of x being factored as much as possible? Well, it's because the type of factors that it has will change the way that we do the actual partial decomposition. So for example, let's say we have some p of x being divided by some q of x, and we managed to factorize q of x nicely. So let's say it was x plus 1 times x plus 2. Now these are the best case scenarios because this is what is known as non-repeated linear factor. So non-repeated means that it didn't repeat itself. So it wasn't like we have x plus 1 times x plus 1. No, we have two different factors. So non-repeated, check. Linear. Linear means that the biggest power of x is 1. So we've got an x to the 1. So other examples of linear factors would be x, x plus 1, 3x minus 2, negative 5x plus 4. So all of these are linear factors. And that is because the biggest power in each of these factors is the power 1. All right, so this is the easiest case. And in this case, when we want to decompose this fraction, it's going to look like p of x divided by x plus 1 times x plus 2 is going to equal some a divided by x plus 1 plus some b divided by x plus 2. And then we do the logic that we did last time. We take the whole equation, we multiply by the bottom, by the thing that we're dividing by, and then off to the races we go, doing all of the algebra in the world. But it's not always the case that we have non-repeated linear factors. This is the easiest case that we have. This is the best case scenario. So what other types do we have? Well, we could have p of x divided by x plus 1 times x plus 1. And now here we have repeated linear factors. And that's because both of the factors are the same and they're both power 1. So the biggest power of x underneath is the power 1. So in this case, we're going to have p of x divided by x plus 1 squared, because that's just x plus 1 times x plus 1. And that's going to look like a divided by x plus 1 plus b divided by x plus 1 squared. All right, so notice that this is actually a little bit different from the one up top. Because it's repeated, we have to have the term in there. And if it was, for example, to the power of 3, then we would have plus c over x plus 1 to the 3. If it was a power 4, then we would need d over x plus 1 to the 4. But in general, whatever the power is, that's the number of terms. So in this case, it's 2, so it's just 2. And then we've got the x plus 1 because we've got the x plus 1. And then because it's squared, we need another one that's squared. We would take the same thing as we did before. We would multiply it by x plus 1 squared on both sides. And then off to the races we go again with algebra. All right. Now there's another case where we have p of x. We've factorized it, the bottom term, as much as we can, but unfortunately, we have a quadratic. So we have something that looks like ax squared plus bx plus c, and we can't factorize it anymore. So to keep things simple, let's say it looks like x squared plus 1. Now this right here is quadratic. It's not linear because the highest power of x is 2, and we can't factor it. There is no way to factor x squared plus 1 without using imaginary numbers. And the moment we start using imaginary numbers, the moment we start getting the square roots of negative numbers, we're stuck. Well, I mean, we can do stuff, but not at this level. That's imaginary numbers. We're not doing that. For this particular case, x squared plus 1 is as simple as it gets. We cannot factor it anymore. So that means that the bottom factor is quadratic, and we're stuck. So in this case, what we're going to do is we're going to have p of x divided by x squared plus 1, and that's going to look like ax plus b divided by x squared plus 1. So because the bottom polynomial is of power 2, the top one is going to be 1 smaller. So for example, if it was p of x divided by x cubed plus 1, then in that case it would be p of x over x cubed plus 1 would equal ax squared plus bx plus c divided by x cubed plus 1. So whatever factor you're stuck with underneath, look at the biggest power. In this case, it was 3. That means that the one up top has to be 1 less, so a power of 2. And we include all of the possible terms it could have. It can have some term of power 2. It could have some term of power 1, which is x to the 1, so just x. And some term of x to the 0. X to the 0 is just 1, so that's why the c is hanging out by himself. Right, so whatever the power is at the bottom that you can't factor anymore, you have to include the whole thing. So in this case, it's usually easier to break it into ax over x squared plus 1 plus b over x squared plus 1. Literally all I did in this middle case was I just took the fraction, split it into 2, keeping the denominator the same, and then I multiply both sides of the equation by that factor. And then we're off to the races again with the algebra. And then in the bottom case, again, we would multiply by x cubed plus 1, divide it all out, multiply it all out, and off to the races again with algebra. So depending on what the factor looks like, it will slightly change what's underneath the a and the b. So you just have to remember what each one of the cases is and what it looks like. But at the end of the day, the logic is still the same. We still multiply both sides of the equation by whatever the bottom term is, and then we're left with a series of equations that we could solve for a and b. And then once we have values for a and b, we know how to break this big ugly fraction into a set of smaller, easier to work with fractions. So this was kind of like a high-level overview of all of the different possible combinations of factors down at the bottom. And now we're going to work them through with a couple of examples. All right, so we're going to start off with a simple example of a repeated factor. So we're going to have 3x plus 1 being divided by x plus 1 times x plus 1. And we need to figure out how we can break up this ugly fraction into a couple of smaller, easier fractions. So first things first, we've got to go through our checklist. So checklist number 1, is the bottom one a bigger factor than, is the bottom one a bigger power than the top one? Well, the bottom one has an x to the power 1 multiplying an x to the power 1, so that's a power 2. So yes, the bottom one is power 2, the top one is power 1, so we satisfy the first rule. The bottom power is bigger than the top power. Rule number 2, is the bottom one factored out as much as possible? And the answer is yes, the bottom one is factored out as much as possible. So we've satisfied the 2 rules, so we know that partial fractions are allowed. And now that we know that partial fractions are allowed, we need to know what kind of roots do we have. Well, number one, I know they're linear because the biggest powers underneath are both power 1, so I know they're linear. And then the other question I have to ask myself is, are they repeated? And in this case, yes, they are repeated. So we can go through the rules really quickly. One, power bottom is the biggest. Number two, factored as much as possible. So yes, and then from there, we ask ourselves what type. So the type is linear because the biggest power of x as a factor is just 1, so it's linear. And then the second type, is it repeated? And in this case, yes, it is repeated. So there's a couple of questions we have to ask ourselves when we're first doing partial fractions, and then once those questions have been answered, we can run off and do a whole bunch of algebra, which everyone loves to do. So we've got repeated roots, so that means that the expression on the left-hand side is going to look a little different. We're going to have a divided by x plus 1 plus b divided by x plus 1 squared, because again, they're repeated. There's 2 repeats, it's a power of 2. If there was 3 repeats, then there would be a power of 3. But right now, it's just a power of 2. So what we do is we take this whole thing and we multiply by the bottom expression. So we multiply by x plus 1 squared. Because I don't want to write x plus 1 times x plus 1 again. I just throw a little square on top. And from that, well, the bottom terms cancel out on the left, so that the left-hand side becomes just 3x plus 1. Now, on the right-hand side of the equation, there's 1x plus 1 at the bottom, but 2x plus 1's at the top. So I'm going to be left with 1x plus 1 at the top. And then for the second term, x plus 1 squared, x plus 1 squared, dividing multiplication, they cancel out, so we're left with just a lonely b. Next, we break up this expression right here into 2 different expressions. So expression number 1, which is the x's, so we're going to have 3x on the left-hand side, or all of the x's. And on the right-hand side, I've got a times x, so that's it, because the b doesn't have any x terms. And from that, we get an answer right away, that 3 is equal to a. Now in red, we're going to do all the non-x terms. So on the left-hand side, I get 1 is equal to, because on the left-hand side, the only non-x term is the 1. Now on the right-hand side, I've got a times x plus 1. So when I multiply the a, I'm going to get ax plus a. So I'm going to have a. And then the b is the only non-x term left. So that's going to be equation 2. So equation 1 is all the x terms. Equation 2 is all the non-x terms. If we had an x squared term, well then we would have an equation with x squared terms only. But that's not the case right now. So remember, what we do is we solve equation number 1 for one of the variables, which we already did. And then we plug that into equation number 2. So that's actually going to give us a third equation. Third equation, which is really equation number 1 plugged into equation number 2, gives us equation number 3. So we're plugging equation number 1 into equation number 2. Well, equation number 2 on the left-hand side starts with 1. Now, wherever I see a, I know I can replace it with a 3. And then b is still b. So it looks like I have 1 is equal to 3 plus b, or in other words, I have b is equal to minus 2. And from our previous equation 1, I know that a is equal to 3. And look at that, I have my 2 answers. Which means that if we wanted to check our answer, if we look at this term over here, we have a, which is 3 divided by x plus 1, and then b, which is minus 2 divided by x plus 1 squared. Now, from the fractions video, if we want to add or subtract two fractions together, we need to make sure that the bottoms match. So in this case, they don't. So I'm going to make the bottom of the left-hand fraction match the other fraction. So we're going to do that by multiplication. So I'm going to have x plus 1 divided by x plus 1 times this factor right here, which is 3 of x plus 1 minus 2 times x plus 1 squared, which is going to equal, well, 3 times x plus 1 divided by x plus 1 times x plus 1, that's just x plus 1 squared. So the first fraction just looks like this, and then the second fraction is already the way we want it. Hooray! So what are we doing now? Well, now we actually combine these two fractions. So I've got 3 times x plus 1, so in other words, 3x plus 3, because it's 3x, and then the 3 multiplies the 1, minus 2 from this guy, and the whole thing, because the bottoms match, is x plus 1 squared. 3x plus 3 minus 2, well, that's just 3x plus 1, and we divide by x plus 1 squared, which is 3x plus 1 divided by x plus 1 times x plus 1. And look at that. We took our two simple fractions, and once we combined them, we got the big ugly fraction that we started off with. So we can see that this expression in black at the very top is true when a is equal to 3 and when b is equal to minus 2. So whenever you're doing partial fraction decomposition, we can really quickly check our answer by recombining the two little fractions that we broke apart. And then when we recombine them into one big fraction, we should end up getting what we started in the first place. So right now that we haven't done any algebra, maybe it doesn't look like 3x plus 1 divided by x plus 1 times x plus 1 is easier to work with than 3 over x plus 1 minus 2 over x plus 1 squared. But once we start doing algebra, you'll see that it's actually the case that the term in black is way easier to work with than what's inside this blue square right over here. So the logic is still the same. We multiply both sides of the expression by the bottom term. We end up getting one little expression highlighted under blue. That one little expression lets us create two equations, one with the x's, one without the x's. We solve one of these two equations for one of the variables, then we plug it into the other equation. So in this case, we solved for a in equation 1, plugged that into equation 2, which gave us a third equation in purple. That third equation now only depends on b, which means we can get an answer for b. We have an answer for a, we have an answer for b. We now know how to break this big ugly fraction into two smaller fractions. And if we wanted to check our work, we can recombine the two little fractions and we will get the big ugly one that we started off with in the first place. Our final example will cover the final type of partial fraction decomposition, and that is when the bottom term has a quadratic factor. So let's say we have 3x plus 1 divided by x plus 1 times x squared plus 2. Now, as always, we check our rules really quickly. Is the power of the top smaller than the power at the bottom? Well, the power at the bottom is a power 1 multiplying a power 2, so that's a total of a power of 3, and the top, the biggest x power is just 1. So yeah, our first rule's checked. The top power is smaller than the bottom power. All right, question number 2. Has the bottom been factorized as much as possible? Well, in this case, it has. We've got x plus 1, can't simplify that anymore. We have x squared plus 2. We can't factor that with real numbers. We'll have square roots of imaginary numbers, square roots of negative numbers, which involve imaginary numbers, which is not something that we can deal with right now. So this is as small as it gets. So yes, our 2 rules for our partial fractions allowed have been checked off. The question becomes, what kind of roots do we have? Because the type of root that we have is going to determine what kind of partial fraction this is going to look like. So I have a linear factor and a non-linear factor. So that means that we're going to have the quadratic and the linear at the same time. Bonus point, there is no repeated factors, which is nice. So the linear factor is always going to look like just some constant divided by the x plus 1. And now the second factor is quadratic. Its biggest power is a power 2. So because the biggest power is 2, that means that the factor on top is 1 smaller. So it's going to be power 1. So we're going to have bx plus d divided by x squared plus 2. All right, so the reason I used d instead of c is because sometimes when you're using a capital C as a variable, it can kind of look like a parentheses, and I just wanted to avoid confusion, so I skipped the letter C, went straight to d, but I want to make it very clear. The reason that the top one is bx plus d is because the bottom one is of a power 2. A power 2 polynomial at the bottom means a power 1 polynomial up top. And because we have a power 1 polynomial up top, we have to include the general case where the power 1 also has a non-x term. Or in other words, it has an x to the 0 term. Because anything to the power of 0 is just 1. So for example, if it was x cubed plus 2x plus 2, well, the highest power is 3, so that means I would have to drop the top one down by 2. So in this case, it would look like ax squared plus bx plus c plus d. So power of 3 means that the top is only a power of 2. And then because it's a power of 2, we need to include power of 2, power of 1. Oh, I didn't need to put the d there, my bad. So because it's a power of 3 at the bottom, the power of 2 at the top needs to have power 2, power 1, power 0 meaning no x's. But in this case, it's not a power 3, it's just a power 2. I just wanted to make that extra clear. So what do we do next? We multiply both sides, like before, by the term at the bottom. Multiply in, and what will we get? Well, the left-hand side is being divided by the entirety of the top, so that means that it cancels out nicely, and we just get 3x plus 1. Now a is being divided by x plus 1, so the x plus 1 is going to cancel out the x plus 1, and we're left with a times x squared plus 2. And then finally, we're going to have the bx plus d is being divided by x squared plus 2, so that's going to cancel out, and we're going to be left with bx plus d multiplied by x plus 1. All right, and now the next step is we bring in the a's, the b's, we multiply everything out so that we can collect terms later. So we're going to have 3x plus 1 equals ax squared plus 2a plus, and then we've got to multiply these two bracket terms together. So we're going to have bx squared plus bx plus dx plus d. And now we're going to collect terms together to make this easier to analyze. We're going to have 3x plus 1, and and we're going to have two x squared terms. So we're going to write those first. So we're going to have ax squared plus bx squared. So that gets rid of these two. Next, let's take a look at the x terms. We've got a b and a d. So plus bx plus dx, boom, boom. And then the non-x terms, 2a plus d. Now, in my personal life, I'm pretty messy, but whenever I'm doing math, I try and stay as organized as possible because that's going to make the whole thing a lot easier to work with if everything's nice and clean. So what I mean by that is I grouped the x squares together, then the x's, then the non-x's. You can group it any way you'd like. I would just highly recommend that you find a way that makes sense to you to group things so that it's easy to work with. So, like before, we took the whole expression, multiplied by all of the factors at the bottom, and then we worked it all out, and then we split it up depending on the x terms. So for example, the x squared terms are going to give us an equation. So we notice that on the left-hand side, there is no x squared term. So that's just going to be 0. Whoops, 0. And that's going to equal, well, ax squared plus bx, so that's just going to be a plus b. Sweet. Then we're going to have an x term. And the x term is just b plus d on the right-hand side. And on the left-hand side, we do have a term with an x. So we're going to have 3, because it's 3x, equals b plus d. And then finally, we've got the non-x terms. So that's an x to the 0 term. And we're going to have 1 on the left-hand side. And that's going to be the a and the d. So it's 2a plus d. Now this is going to be equation 1, equation 2, equation 3. So here we have 3 equations, 3 variables, and as long as we have an equal number or greater number of equations than we do variables, we know it's solvable. Here, this is very solvable. There's a couple different ways to do this, because again, with algebra, you have the freedom to do basically whatever you want in whatever order you want, so long as you follow the rules. So as long as you follow the rules, you should be all good to go. I'm just going to lower this for a quick second to give ourselves a little bit more space to work with. So for our purposes today, I'm going to do substitutions to solve this system of linear equations. So when I'm trying to solve for a system of linear equations, what you're trying to do is you're trying to solve one of the equations for a variable and then plug into another one. So for me, right here I see that equation number 3, the one in green, depends on a and d. And I see that equation number 2 in red depends on b and d. So what I have as my intuition, what I like to do is I'm going to go, okay, I'm going to solve the green equation, or equation 3 for d, and then I can plug that expression into equation 2, because then that way I'll have an expression that depends on a and b, and equation 1 depends on a and b, and then I know I'm cooking with gas. So I'm trying to get rid of that d, and that's what's going to let me do that. So let's do it. So we're going to solve for equation 3 for d. So I've got 1 equals 2a plus d. So I see that d is being added to by 2a. So remember, additions get rid of by subtractions. So I've got 1 minus 2a is equal to d. Okay, now I'm going to plug this expression for d into equation number 2. So I'm going to put that into equation number 2, or in other words, the red equation. So I'm going to have 3 is equal to b plus, and then wherever I see the d, I'm going to throw down a bracket, and I'm going to write out the expression in green, because I know that d is actually 1 minus 2a. Just like that. Or in other words, 3 is equal to b plus 1 minus 2a. Great. So now if we look at this latest expression in red, we've got an equation that depends on A and B. And if we look at the expression in blue, it also depends on A and B. So for equation number 1, we're going to have 0 is equal to A plus B. And if we compare these two right here, we'll notice that they're very similar to each other. Two expressions that depend on the same two variables. Now, I could try and solve the red equation in terms of B or A, or I could solve the blue equation in terms of B or A. Now, for me personally, I think it's going to be a lot easier to work with the blue because it's a lot easier to isolate than the red one. All right, so I would, again, with the algebra, you can do it in whatever order you want, but there's usually an order that's easier than the other, and my personal tip is just do the one that's easiest for you, because you're not going to get brownie points on a test for doing it a harder way. From blue, we can really quickly see that B is just minus A. Or we could also say A is equal to minus B. You know, dealer's choice. You get to pick which of these two you want to do. But for me personally, I'm going to pick A is equal to minus B. So I'm going to use this expression right here. So the red expression is 3 is equal to B plus 1 minus 2. And then wherever I see the A from the blue expression, I know that I can substitute a minus B. So from there, I'm going to have 3 is equal to B plus 1, and then we're going to have minus 2 times minus B. Those two are negatives are going to cancel out, and we're going to get a plus 2B. And then from here, we've got one equation with just the one variable. So we can really quickly see that it's going to be 3 is equal to 3B plus 1. And then from here, we get a very simple B is equal to, you take the 1 over, that's going to be 2. So that's just going to be 2/3. And now we already have an expression for A, which is really nice. In blue, we know that A is equal to minus B. So then we can really quickly write A is equal to minus 2/3 because A is just the negative of B. And now the nice thing is in green, we've got an expression for D that depends on A. So we're going to have 1 minus 2 times, and then wherever we see A, we can plug in minus 2/3. And that's equal to D. So we're going to have 1. And now negative 2 times negative 2/3, negative and a negative turns into a positive. So we're going to have plus 4/3 is equal to D. Or in other words, we're going to have 7/3 is equal to D. So D is equal to 7/3. And just like that, we've managed to find values for A, B, and D that satisfy this top expression in black. So we know that we can break apart this equation, this big, I was going to say ugly, but I like polynomials. But I mean, admittedly, it does look a little complicated. So we've got this big complicated fraction, and we've turned it into two smaller fractions, which if we were doing calculus and we wanted to integrate or differentiate, it's way, way, way easier to handle two small ones as opposed to one big one like this. So just like that, we've managed to break apart one big ugly fraction into two pretty ones with the values of B equals 2/3, A is equal to negative 2/3, D is equal to 7/3. And if you want to check your answer, all we have to do is plug our values of A, B, and D into A, B, and D, and then combine these two fractions. The easiest way would be to make the factors at the bottom look the same. So I would multiply the first term by x² plus 2 on the top and the bottom. I would take the second term, multiply by x plus 1 at the top and the bottom. That way the bottom terms match, or in other words, it's basically just cross multiplication. So you can plug A, B, and D, cross multiply these two fractions, and then after a little bit of simplification, you'll end up getting the fraction on the left. So whenever you're doing partial fraction decomposition, you can really quickly check the answers. Now, I realize that there's a lot of colors on the screen and it could look a little bit complicated, but the idea is basically give yourself a system of equations, in this case 3, and then from there you take one expression, solve it for one variable, plug it into the other. Because what you're really doing is you're getting rid of one of those variables. So we're trying to chip away at these equations so that we get fewer and fewer variables until we're down to this red case where there's just the one variable left. So again, the logic is solve equation 3 for D. So now we have D replaced with A. So when I looked at expression number 2, I realized, hey, I can get rid of my D and replace it with A, and now I've got an equation 2, which is this guy right here, that looks like an expression of B and A. So now instead of having 3 variables, I only have 2 variables. Then we do the same thing again. We solve one of the 2 remaining variables. Sorry, we solve one of the 2 remaining equations for either A or B, your choice. Remembering that in this blue case, we had the choice of either making B equal negative A or A equaling negative B. I chose to substitute A is equal to negative B because I knew that the negative and the negative would cancel, and I personally hate dealing with negatives. So if I've got a chance to turn negatives into positives, I jump on it immediately. You could have done it with B equals minus A, no problem there. If that's what you'd rather do, hey, that's the beauty of algebra. We each get to do it the way we like best. But for myself, I know that negative signs have kind of bit me in the butt more times than I can count. So if I can preemptively get rid of them, I will. But again, this is a little bit complicated. I acknowledge that there's a lot of colors going on. When there's 3 equations, the substitution method starts to get a little bit more convoluted. But again, just want to stress, the whole logic is still the same. You're doing substitutions to get rid of variables, and you're just chipping away, chipping away, chipping away until you have one equation with one variable. And then the nice thing is, after you get that first variable solved, which in our case was B, the rest falls out really quickly. So it's really just that first variable that's really kind of tricky to find. And then afterwards, you've got expressions for what the other ones have to be. So after you get that first one, after you get that first hard one, the rest is going to be a lot easier. I'm going to include a bonus video on how to do these systems of linear equations in a slightly easier way. It's a technique involving matrices. I'm not going to include it in this video because this video is already getting pretty long on me, but I'll put a bonus video at the end of the algebra playlist about how to solve linear equations with matrices and what's called Gaussian elimination. So it'll give you a nice systematic, kind of easier way to solve these equations. But I myself, I love substitution. I love it. Makes me feel like a wizard, that I can start taking apart all these things and put things inside of other things and get an answer at the end of the day. But I just wanted to give you guys options and let you know that if you didn't quite like the substitution method, there is a better method coming out very soon. Now, that is the end of our last example because it covers a quadratic mixed with a linear. So you get to see how you have multiple different types of roots interacting with each other. And the next thing is everyone's favorite part of the video, the extra fun bonus problems. All right, so for the extra fun bonus problems, I've given you guys 3 sets of different problems. So for the top 2, we want long division. For the middle 2, I've given you factorization through division. So notice that these ones are equal to 0, so that when you factorize, you know that each of those factors has to add up to 0, unlike this top one, which doesn't have an equality sign. So with the long division, you're working with expressions to make them easier. The bottom one, we're factorizing because there's an actual equals 0 at the end, and we could get solutions if we wanted to. And then finally at the bottom, we have partial fraction decomposition, where I've given you a combination of non-repeated linear roots and then a combination of linear and quadratic roots. So just take these and break them into a couple of smaller, easy to work with equations. I'll give you a second to pause the video so you can figure out the problems on your own. And then as always, I'll throw up the answers on screen in purple. All right, as always, the answers are in purple. So for the long division, it's fairly straightforward, just long division. For the factorizing, remember that we can try and guess a solution to the actual polynomial first in order to get one of the factors. And then once you know one of the factors, you can just divide the original equation, the original polynomial of power 3, by that one factor to get the rest. So for this first one, I would recommend trying x equals 1 or minus 1 first. You'll see which one works out. And then, for example, if you had plugged in minus 1 into the black equation, you would have realized that you would have gotten a wrong answer. But if you had plugged in x equals 1 into the black trinomial, or the polynomial of power 3, you would have ended up getting 0 equals 0. We know that x equals 1 is an answer, so that x minus 1 is one of the factors. Then we could have divided x to the 3 plus 5x squared plus 2x minus 8 by x minus 1, and then we would have gotten the rest of the factors after that division. For the second factorization through division, very similar. Try out easy values of x to plug into the formula. You'll end up finding one fairly quickly. And then once you have an answer that gives you 0 equals 0, you know what one of the factors is, then you take the original, divide by that known factor, and you'll get something that you can factorize on your own. So factorizing through division, remember you guess one to give yourselves a factor, and then it's just long division, like up above. And then finally, for partial fraction decomposition, the first one's fairly straightforward. It's going to look like some a divided by x plus 2 plus some b divided by x plus 3. You do a whole bunch of algebra, you'll get some numbers for it. You can combine the purple terms through cross multiplication, and I promise you'll get the black ones, but if you want to check for yourself, more than free to. For the second one, the values of a, b, and d were a little bit different. So I left them up top so that you could very quickly see what they have to equal. So the roots being, the first root being linear, looks like a divided by x plus 1. So the a is equal to a quarter. And then finally, this one, the second root is quadratic. So it's going to look like d plus bx divided by x squared plus 3. So the d term that doesn't have an x is going to be 13 over 4, and then the b term with an x is going to have b equal to minus 1 over 4. So if you guys have any questions, please feel free to throw them down in the comments section, and I hope that you guys had a good time doing all of this practice problems. Hopefully divisions by polynomials at this point will not only look not too bad, but might actually be fun. I hope you guys have a good rest of your day. Just try your best and have some fun.